Sorry? The relic students. The wimps. Okay, we'll continue with the thermal dark matter. And the idea is to start and maybe finish non-thermal dark matter. So I'm very late in what I want to cover. So remember that we discussed, when discussing WIMPs, we discussed a lot about the freeze out, and when I say freeze out, I mean freeze out of chemical reactions. So TFO corresponds to the freeze out of chemical reactions, so number changing interactions. But there's also another equilibrium, not chemical equilibrium, but the kinetic equilibrium. And remember that kinetic equilibrium refers to elastic interactions. So the chemical interactions change the number of dark matter particles, so you really fix the dark matter density. And the kinetic equilibrium fixes the temperature. So when you're in equilibrium, the two sectors share exactly the same temperature. After the breaking of the kinetic equilibrium, the two sectors will have temperatures well defined, like the really black body spectrum, but with a different temperature. So in the case of WIMPs and SIMPs, we'll see afterwards, we have this hierarchy. The chemical equilibrium is broken very early, I mean much earlier than the kinetic freeze out. So T freeze out, X freeze out is around 20, say 20, 25, 30. However, this X freeze out, remember that X, I define it like basically M over T. So the X kinetic is, for WIMPs, is very large, is 100,000, 10 to the 4, yeah, something like this. So the idea is to see what happens if we can start playing with these hierarchies. So we typically need M to be larger than T freeze out because we want dark matter to be produced, to be cold, so to be produced when non-relativistic. So this hierarchy is always fixed. However, this kinetic decoupling, we will play with it. So it could be here, like in the case of elders of this hierarchy, or it could be when dark matter is non-relativistic, like in the case of cannibal. And that's exactly what we did yesterday. So what we're doing is using this instantaneous decoupling approximation, exactly what we did for WIMPs, for instance. So we say that what the yield, remember, Y is the comoving yield is defined as the number density over the energy density, entropy density of the standard model, right? So we define, we use the instantaneous approximation, that instantaneous decoupling approximation, right? So we see that it failed like in a factor of maybe a few, maximum order of magnitude. Gracias. And so using this idea, we solve it for WIMP. So I just copied here the expression that we found, right? For WIMP, just to compare with the others. So the final yield, so the yield at present, depends on X freeze out, and if in particular you find this exponential dependence due to the Boltzmann suppression when dark matter becomes non-relativistic. So that we saw maybe in the second lecture, so on Tuesday. And this was really the end of yesterday's lecture, right? So the case where you have these hierarchies. So the case of elder and cannibal dark matter. So we found these expressions, and yes, I want to show you, just to emphasize this point, is that in the case of elders and cannibal, as we are breaking kinetic equilibrium earlier, so it's not at the moment of chemical freeze out, the two sectors don't share the same temperature, so we have an increase on temperature. In the elder case, this increase is kind of controlled because there's only a small period when you have an increase of temperature. However, in the case of cannibal, as you're breaking kinetic equilibrium when dark matter is relativistic, you have a maximal increase of temperature. And that's what we saw in that plot, and we discussed yesterday. And we can keep track of this relative increase of temperature, just assuming that, just considering conservation of entropy, right? Separate conservation of entropy in the two sectors. So that's what we saw yesterday. And we wrote these two expressions, and we just want to walk you, to guide you in these expressions. So first, in the case of elder, it's basically the same structure. However, there's a big dependence, so it will depend on X prime freeze out, right? So the moment where dark matter goes out of chemical equilibrium, I put the prime because it refers to the temperature in the dark sector. But it also depends on xk. And there's a big dependence, big exponential dependence on xk. And that's a kind of surprising because after all, so that means that it's basically these elders basically depend on the moment when the kinetic equilibrium is broken. So remember that kinetic equilibrium refers to the temperature, the last moment where the two sectors share the same temperature. Right? So this at first sight is surprising. However, remember that if this xk, what is giving you is like the temperature in the dark sector, and the temperature of the dark sector, I mean, the temperature is basically a proxy of how many particles are there, right? For instance, for photons, the number of photons is, density is like T cubed, right? So knowing the temperature is, with the temperature, you can reconstruct the number of particles. So that's the case of elders. You have an exponential dependence on the moment of the kinetic freeze out. And for cannibals, the expression is very simple. It will not depend on xk because it goes out of equilibrium when it's relativistic, so we lose all the sensitivity. You only have a dependence like 1 over x prime freeze out, right? And x prime because it's the temperature of the of the dark sector. Okay? So I have a plot of these solutions. So here I'm showing you the values, the required values of xk, so the moment where you break kinetic decoupling and x prime freeze out. For different values of the mass. So the 10 to the, so 1 TeV, I don't see this. 1 TeV, 1 GeV, 1 MeV, and 1 KV, right? So these 4 lines show you the parameter space required in order to fit the whole observed dark matter abundance for the 4 mechanisms. So WIMPs, forget SIMPs for now, WIMPs, elder, and cannibals. So let's go first for WIMPs. We're very used to that. So WIMPs, we know that if we want to fulfill the whole observed dark matter abundance, we need the X freeze out of the order of 20 or so for 1 TeV or 100 GeVs. And that's exactly what we see. So there are vertical lines that mean that for WIMPs, we don't care about when kinetic decoupling is happening. And it corresponds to basically order 20 or something like this. That's for WIMPs. However, if you go to elders, you start to feel this strong exponential dependence on the temperature of kinetic decoupling. And that's what you see here. So it's basically, of course, it's not exactly flat, but at first approximation, it's flat, right? At first approximation, it only depends on xk. There's a small dependence on x prime freeze out, right? So it's kind of flat. However, if you go to big enough values of x prime freeze out, you start to feel that the dependence on xk, and you enter in the cannibal region where you have, again, like a vertical dependence, only that because it only depends on x prime freeze out, right? So here I'm taking an extravagantly large values of x prime freeze out. So typically this cannot be bigger than 50 or something like this. However, I just plot this super large parameter space just to show you the evolution. And I took very small masses also. I mean, this is in tension with Lyman alpha and BBN. However, I just want to show you the whole structure, the whole solution of this thermal dark matter. Okay? I have notes. Okay, and that is interesting because here it is completely independent on the particle physics, right? So I'm not telling you what is the particle physics model behind. So what are the interactions? How dark matter is getting annihilated? How the two equilibriums are maintained, right? This is completely independent. It's just basically conservation of entropy, right? It's kind of arguments. Now let's dig a bit into the particle physics. So we want to know where to compute all these departures of equilibrium. So remember that we defined this gamma annihilations on the annihilation interaction rate, and it was like this sigma V annihilation times n dark matter equilibrium. Also this gamma elastic, which was sigma V elastic times the standard model number density, and these two guys, so these two thermally averaged cross section are basically the same. So this gamma, the interaction rate is very different because the number densities are very different. One is Boltzmann suppressed and the other is not. Okay, however, we can define what we want. Okay, this will take care of the kinetic equilibrium. This will define the TK when you have the kinetic equilibrium. However, for the chemical equilibrium, this is one reaction. So sigma V, remember, this corresponds to 2 to 2. So dark matter into standard model. However, we could have other reactions that guarantee the kinetic equilibrium, chemical equilibrium, sorry. For instance, you could think about 3 to 2 reactions. It's just an example, where the idea is not 2 dark matter particles into 2 standard model particles, but we can imagine reactions like this. So we have only dark matter flowing, particles flowing here, right? What we want at the end is to tune the dark matter abundance, right, to reproduce the observations. So in this reaction, it violates the number of dark matter particles. It's a number density violating. So we're going from 3 to 2 or 2 to 3. I mean, you can imagine any, right? So 5 to 10, it will only also work. So for instance, if you take this example, you can do the same exercise. There's kind of well, the interaction rate is like a kind of generalized cross-section times n dark matter equilibrium square, because we have now 3 particles in the initial state. So this reaction will is the one fixing the moment where the kinetic equilibrium is broken. However, these 2 reactions here, or in general, all reactions that violate the number of dark matter, that modify the number of dark matter particles, are the one that take care of the departure of chemical equilibrium. So that's the idea in this Sims, Elder, and Cannibal. So for WIMPs, you only take into account these reactions, so 2 to 2, 2 dark matter and 2 standard model. However, for the other Sims, Elder, and Cannibal, you have to also care about other processes within the dark sector. And that's the idea of cannibalism. So that's why the name. So you're going from 3 dark matter particles to 2. Yes, so. And also, if you remember what we are having here, this increase of temperature, it could also be understood in this framework. So what you're doing, when you have the 3 to 2 annihilations, you're going, if dark matter is non-relativistic, right, to the moment of freeze out, you're going from 3 particles, non-relativistic particles, into 2 particles that will be relativistic. So you're trading mass into kinetic energy. So you're increasing the dark matter temperature, and that's exactly what we're seeing there, right? So you can also understand it in this perspective. So you're trading mass, so 3 dark matter particles into 2. So the mass is increasing. Conservation of energy means that these guys have a higher energy, kinetic energy. That means higher temperature. That's exactly what we are seeing there. Right. Yes, of course.
There will be like an equilibrium there, right? Or
there
not?
will be?
An equilibrium there,
yes,
between the 2 processes.
Yes, it could have an equilibrium. So yes, I will discuss that afterwards. So you can have, of course, if these guys are in equilibrium, well, okay, we can think that these processes are in equilibrium, meaning that you have the 3 to 2 and the 2 to 2 reactions, and equilibrium means that they happen at exactly the same rate. After the free, yes, okay, but at some point you can have that only one reaction, 3 to 2 or 2 to 3, right? So for instance, when it becomes non-relativistic, dark matter, you will have a 3 to 2 only, because the 2 to 3 is not kinematically allowed. However, in the early universe, you can have exactly the opposite, like creation of dark matter from 2 to 3. And I will show you an example after that. Yes, of course, but that's a good point, thanks. So these kind of objects that they call sigma v squared, because what I have in mind is a 3 to 2. You can compute that. I mean, this seems like a horrible thing, but you can compute, and you expect this sigma v 3 to 2 to have this expression, like a coupling cube times mass power 5. So this is a typical structure. You can compute it actually. And I have, of course, and the Boltzmann equation that you have to solve now will be, I will write it here, but you have exactly the same expression. So the n dt plus 3hn, right? This universal factor minus sigma v 3 to 2. And now I have 3 dark matter particles, so n cube minus n square equilibrium. So it's different. So the Liouville operator is exactly the same. The collision term is different because the particle physics is different. But I mean, you kind of feel, you can understand the structure. However, there's a big difference. Is that now dark matter will depend on its temperature. So T prime is the dark matter temperature. So let me put all the temperatures here. So it's super redundant, but let me do it. Right? However, the universe I want it to be dominated not by dark matter, but by the standard model. So here is T. Right? So a single Boltzmann equation is not enough because you have to keep track of the evolution, of the relative evolution of temperatures. So you can do it, you can have a Boltzmann equation for the energy transfer, but you also know analytically how it should behave, right? That's what we computed yesterday. So even if the structure is basically the same, right? The derivative, Hubble, and the collision term, in practice it's very different because you have to keep track of different temperatures. Okay? So again, you can have an extra Boltzmann equation not for the number density, for the energy transfer, or use this analytical approximation that we did. And it's basically the same. Okay? Right, so, okay, forgot this. So good, so we can solve this equation analytically, and that's basically what we have. So at first sight, it's basically the same as WIMPs, right? So here is y times m as a function of this parameter x, right? So this blue dashed line corresponds to the equilibrium, like exactly in the case of WIMPs, but the equilibrium with respect to the standard model. Yes? However, dark matter has its own temperature, so here this line, this kxd, is what I call xk, correspond to the departure from kinetic equilibrium. So before that, well, I would have put this line basically here. The two temperatures are the same. They are in kinetic contact, so the two temperatures are the same. At later times, you break the kinetic equilibrium, so your dark matter is a bit hotter, right? So this red line corresponds to the equilibrium with respect to the temperature of the dark matter, which is slightly higher. So dark matter is following. It seems that it's not in equilibrium, however it is. It is, but at a different temperature. So here you have the breaking of the kinetic equilibrium, and here is the freeze out, what I call XFO, so the breaking of the chemical equilibrium. So here is not tracking anymore, you can see here, right? So this is the equilibrium with respect to the temperature of the dark sector, and here you get out of equilibrium, so the freeze out, the chemical freeze out, for the case of elders, right? Because this happens when X is bigger than 1, so when dark matter is non-relativistic. For the case of cannibals, it's basically the same. We just move this line here to X values smaller than 1. Okay? But you can do that. I mean, solving this Boltzmann equation, you will automatically find these kind of behaviors. Yes, okay. We also discussed yesterday, maybe also on Tuesday, the singlet scalar dark matter model, remember? It was a super simple model where you only have, you introduce a dark matter and a Z2 symmetry to guarantee dark matter stability. You have the Higgs portal, so a connection between two dark matter and two Higgses. And you also have the quartic. And for WIMPs, we completely disregard the quartic couplings. However, the quartics are there, and you can have not 3-to-2 annihilation, but 4-to-2. And here I'm showing you plots of Feynman diagrams, okay, Feynman diagrams where you have 4-to-2 annihilations of scalars with only the quartic couplings. But you can see that you only have quartic interaction here, 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 and here. And the dark matter is the only particles flowing there. So it's not 3-to-2, but it's 4-to-2, because I want to use exactly the same example that I showed you yesterday. And okay, here I'm showing you the plot of the SIMS. So the SIMS, remember, is the case where you have the same temperature. So the dark, it's exactly a freeze out. It's exactly a freeze out, but within the dark sector. So it's not two dark matters into two standard model. It would be four dark matters into two dark matter. So the dynamics is exactly the same. And also, this hierarchy is guaranteed, so we have exactly the same temperature. So actually, I'm showing you the same plot for WIMPs, but WIMPs are SIMS, exactly the same thing. The WIMPs is basically a freeze out in the visible sector, whereas the SIMS is exactly the same freeze out, exactly the same Boltzmann equation, exactly, wait, I will show you the Boltzmann equation in a minute, the same structure, and the behavior is exactly the same. So I'm showing you exactly the same plot of the WIMPs. These really correspond to WIMPs, but if I produce the plot for WIMPs, you will not see, for SIMS, sorry, you will not see the difference. So for SIMS, in particular, in this case, the Boltzmann equation is super easy. You already know. Sigma V, 4-to-2, N4 minus N2, and equilibrium square. Yes, again, Liouville is exactly the same. Collision changes a little bit because it's another theory. And here is the singlet scalar dark matter. Okay, so we understand that it should only depends on the quartic coupling, because in this kind of process, only the quartic coupling is there. It's completely independent on the Higgs portal, as in the case of WIMPs. So here I'm showing you the parameter space favored by the SIMS. So it's very crowded, so please, okay, I'm recycling this plot. Forget basically everything, so all the lines. So just focus on this thick black line. So here I'm showing you the quartic coupling, right, as a function of the dark matter mass in MEVs. Yeah? So, and this line corresponds to the parameter space required to feed the whole observed dark matter abundance. In the case of SIMS, right, so they have the same temperature. In SIMS, you have exactly the same hierarchy as for WIMPs. So in the moment of the freeze out, the T of the gammas is equal to T of dark matter. And that's always the case in the SIMP paradigm. So yeah, please forget all the other lines. So just focus this. So SIMS is always viable when dark matter is kind of light with respect to the standard WIMP. So when it's in the MEV ballpark, right, it's also limited by perturbativity. So all SIMS have to be typically light and yes, MEV-ish, right? And it only depends on the coupling within in the dark sector. So in particular, in this model, depends on the quartic coupling, not in the Higgs portal. Okay, but the idea is again is very very similar. Of the case of WIMP is basically a WIMP within the dark sector. Yes.
That is two singlets, no? Interaction point, like because we have the quartic.
Yeah, like the mass. Yeah.
Why we can have like a 3-to-2? A 3-to-2 with
no. Well, not exactly in this theory, because here we're assuming they have a Z2 symmetry. So Z2 forbids this kind of interaction with an odd number of particles. So that's why, okay, this in this case is simpler. However, I just want to recycle the example we're using. So in this case, where you have a Z2, you cannot have 3 to 2 annihilations. So you can have 3 to 2, for instance, if you use a Z3 symmetry, or if you use non-abelian dark matter. So it will be like you can have like gluons, for instance. You can have this kind of process, or Z's, right? So if it's non-abelian, you can have 3 to 2 annihilations. Yes, well, maybe for sociological reason, this Z2 is more found in the literature. So, for instance, if you think in the neutralino, right, you have R parity, you can have this process. Of course, they're completely subdominant. That's another story. But this process for the neutralino dark matter, you can have 4 to 2. Subdominant, yeah, but they're there. But that was not your question.
No, I was just thinking because of the mixing with the Higgs, so if we could have like...
No, here, remember, we have like the Higgs portal, what they call HS. It was Higgs square S square plus lambda S power 4. That's it, and the mass.
Okay, thanks.
Yes, because of the choice of symmetry, so we have these 2 parameters only. Yeah. Yes, exactly. There's no mixing. Yeah.
Yeah, you don't allow a BEV for the S.
Yes, sorry.
Okay, that's my confusion.
Okay. Yes. This guy, yes, it's completely stable. It's not taking a BEV. There's no mixing.
Okay, so it's completely secluded.
Well, no, because you have this portal. Well, here, yes, at this point, it's completely secluded. If you put this portal to 0, and you forget gravity. Yeah. So for SIMS, okay, first comment. For this, I could assume that this is completely 0, this is completely secluded. But however, remember that we have to guarantee the kinetic equilibrium, right? So that means that this coupling cannot be exactly 0. It has to be, could be very small, but it cannot be 0 because you want for SIMS to have the same temperature. Yeah? So what we want is these guys to be dominant. Okay, for SIMS, let me put it again. We want, so this gamma 3,2 to be much bigger than gamma elastic annihilation. Yeah. So we typically have you always have this hierarchy because of number densities. One is Boltzmann suppressed and the other is not. It's a power law. And here you can have it if you have big couplings and small couplings. So that's and we have different couplings, right? See, if this coupling is very large, so that's the idea of strongly interactive massive particles or self-interactive massive particles to have a sizable quartic coupling, for instance, here. Whereas this Higgs portal could be very suppressed, right? So that's exactly the hierarchy that you require. You want kinetic decoupling not to be very late. Like exactly, this seems is exactly a WIMP, but within the dark sector. Had to be smaller because you want the Frieza al revés. Yes, sorry. Yes.
And then you don't need to also check the temperature because you can assume it's...
Exactly. No, it's not that you're assuming. I mean, by construction, you're imposing this. Of course, that's something that you have to check. If not, it will just be, it's fine, right? But it will be an elder, what we call elder. Yeah, that's the only thing. Good, thanks. More questions? Yes, we find the two strongly or self-interacting. Maybe the idea, I mean, you have big couplings, order one couplings. So strongly, but also I think it's better to call it self-interacting dark matter because you're really using the self-interactions. Yeah. Okay. I think that was it for yes, for the thermal side. Yes, so this cannot be zero, right? Because you still want to have kinetic equilibrium. Yeah. You still have elastic scattering. You can have direct detection, for instance, via Higgs. Yes, so this is not the best model for doing SIMS because you need light dark matter, right? So you have to be always in the MEV, sub GeV for sure. It interacts via the Higgs. So in principle, you can have elastic scattering with electrons, but this Yukawa, the electron suppressed. So, I mean, yes, for detection, it's not, I mean, don't have, you will not like it, right? Okay, that was everything I wanted to tell you about thermal dark matter. And after thermal dark matter, what comes? Bravo. Okay, so this is huge non-thermal dark matter. Basically, I mean, we have many mechanisms. Kafir already on Friday discussed one, remember? Fuzzy dark matter, ALPS, fuzzy dark matter. Okay, so that's all that I wanted to tell you about fuzzy dark matter because it was already discussed. So check. Questions, comments about fuzzy dark matter? FIMS. So we have seen WIMPs, FIMS, SIMS, so all the letters. So FIMS correspond to, maybe I should have written this, there's no room. Okay, strongly interactive massive particles or self-interacting massive particles. FIMS now, the F is for feebly interacting massive particles. Yeah. So all about thermal dark matter is that we want to have dark matter that reach both chemical, in particular chemical, and also kinetic equilibrium with the standard model, right? For FIMS, or in general for non-thermal dark matter, we want to avoid such an equilibrium. Yeah. And the idea of FIMS is very easy. So we start again with WIMPs. So the Boltzmann equation of WIMPs, I will write it like for the, not the first time, plus 3HN. And how can we make this guy, how can we avoid the thermalization of dark matter? So in principle, it's very easy. We can just take very small couplings, right? Because this is a collision term, the one that guarantees or not the thermalization. So for FIMS, actually, yes, okay, so the idea is to have a very small interaction rates. And then we'll see how can we guarantee that have small interaction rates, so small gammas, if you want, so small cross sections. So there are two ideas. Well, it's basically the same, but it comes in two different flavors. So the infrared FIMS. And the idea of FIMS, of the infrared FIMS, is very easy. You will see. Where is it? Here. So checklist. So we want for the infrared WIMP to use renormalizable operators. Yes. So for instance, we can use exactly this theory. So singlet scalar dark matter model. So when we get small cross-section, small interaction rate if we take small couplings. So very easy. And we'll see small couplings typically means 10 to the minus 11 or something like this. For instance, lambda HS in the case of the single scalar dark matter model. The masses, you will see that the mass range is huge. Remember, for WIMPs, we were limited by perturbativity. So the couplings at some point were beyond the perturbativity range, so we had to cut WIMPs at a mass of 130 or so TeVs. Here, the couplings are always very small, so we have basically no upper bound. So we want to be smaller than, lighter than M Planck. Well, it's just, I mean, a big number, right? And they have to be heavier than MEV or something like this to avoid problems with Lyman alpha for sure and with BBN. So the mass range for FIMS is much larger. And it's called infrared. Basically, we should have started by that because the bulk of the dark matter production, T3Z, let me say it like this. So the bulk of the dark matter happens in the infrared, so small temperatures. So typically when the temperature of the order of the mass scale of the problem. So mass of the dark matter or the mass of the mediators. Actually, it's the maximum of this. The maximum of this. So, yes. And also, here, dark matter is not thermal. That means that it will not reach equilibrium. It will not reach thermal equilibrium. Dark matter is not thermal. So that means that we'll have a dependence on the initial conditions. And that's important. It's very different with respect to WIMPs, or in general, thermal dark matter. Remember that we say that for WIMPs, we have no dependence on the initial condition. Everything was erased because we reached this attractor, which is the equilibrium. However, for FIMS, we will not reach equilibrium, so we'll have always a dependence on the initial condition. And this, as again, was I told you last time, this is good and bad. Is difficult because when solving the Boltzmann equation, solving this first order differential equation, we'll have to input the initial conditions. Initial condition basically is the details of reheating, the details of inflation maybe. So what's the original dark matter abundance after inflation, after reheating? What is the reheating temperature, for instance? Things like that we have no control. So from the technical point of view, this is a disaster because we have to take, the result will depend on the initial conditions that we don't know. However, once dark matter is detected, if dark matter happens to be a FIMP, or in general, non-thermal dark matter, this is a blessing, right? Because in principle, so dark matter will be a messenger from the very early universe. So we could think that we could maybe extract information about reheating, yes, reheating temperature, or details of inflation. So again, this is a two-edged sword. The same plot of WIMPs, remember? So y as a function of x, dashed line corresponds to the equilibrium. Dark matter tracks equilibrium and at some point frees out, goes out of chemical equilibrium. That's WIMPs. Now on the right-hand side, you have the typical evolution of FIMS, of infrared FIMS, right? So again, the dashed line corresponds to the equilibrium, and the three lines correspond to the solution of this Boltzmann equation, just taking small couplings for the three values of the coupling. So you see dark matter is produced very slow, right? It reaches a plateau when x is or the order 1. So at low temperature, so in particular when the temperature of the standard model is of the order of the dark matter, so when x is order 1. And then you have a plateau, and you expect this plateau to reproduce the observations. So technically, of course, forget about the initial condition. It's exactly the same Boltzmann equation, right? The only thing is here, this term, okay, dark matter, its density is always very small with respect to the equilibrium. So you can typically neglect this part, right? If you neglect this part, what you will get is that it's a positive, so production sigma V times n equilibrium square. So dark matter is basically only being produced. You don't have sizable annihilations. So production and annihilation happen, but not at the same rate, right? So and this, the production is basically, and the dominant and by far. And that's a typical evolution of FIMP dark matter, infrared FIMP dark matter. Okay? Exactly, yes, exactly. So it's exactly this reaction, but happening in this direction. Yes. So technically, it's exactly the same. If you have the cross section for WIMPs, you have the same for FIMPs. So technically, it's exactly the same code if you want. Exactly the same code. You also have to be careful with the initial conditions. Okay, so if you remember, it's exactly the same Boltzmann equation, so it's just a sketch. So I'm showing you the value of the coupling in the x-axis. So this will be like the Higgs portal coupling in our case. And on the y-axis, I have the dark matter abundance, so normalized to the value that we observe. So we want to be here basically in 1. So what I'm telling you is that if you take exactly the same model, there will be 2 solutions. One solution corresponds to the freeze out, so WIMPs, when the coupling is order 1. Another solution will appear when you have a very suppressed coupling, right? So and this is the evolution, right? So very small coupling, you have an underabundance, then you overproduce, and then you have an underabundance again, right? So last time we discussed this case, so very big couplings correspond to big interaction rates. Dark matter is in equilibrium for longer, you have an underabundance. And okay, the opposite happens in the case of freezing. Okay, yes?
When you say it's dependent on the initial conditions, they're saying that, for example, when we're solving the differential equation, I need to set initial condition to solve this. And they're saying that, for example, if you pick, for example, the blue curve, if I change this initial condition, it will end up in a different, for a different Rayleigh density at the end.
Exactly.
So in the next plot, when you show the Mesa plot, for example, so this also, the left part also depends what your, if you change this initial condition, it can change
exactly. Yes. So let me do something like this. So like artistic view. So if I change the initial condition, maybe it will be something like this, and at this point, right, something like this. So this part is independent. This part will depend.
Okay, but it changed. But people don't usually show this information about, like, this is important when we are doing this?
No,
show
because,
the initial condition.
yes, what people will do, and what I'm always doing here, is I say that the N at high temperatures, N initial, I don't know how to define it, initial, when temperature is very high with respect to something, is 0.
Exactly.
And this kind of makes sense. I mean, that's a first approach. You want to study the FIMPs, so you assume that the FIMPs is the only mechanism that is there. Of course, for an academic point of view, this makes completely sense. So let's focus on FIMPs. In reality, this makes no sense at all, because there are other processes that, for instance, gravitational process, right? So dark matter, it could be very small, it could be very suppressed, it could be subdominant, right? But say that it's exactly 0, that it's the standard assumption, it makes no sense. It cannot be like that.
For example, in a realistic model where I take into account, I don't know, all these gravitational particle production, everything, can I start guessing in a reasonable way, like just like the initial guess? Can I make a computation that this initial abundance coming from, I don't know, primordial black hole evaporation, the expansion of the universe, all these other mechanisms, and then I have a number that I start, and then I freeze in. Can I do
Exactly,
that?
that you can do.
Ah,
Or
okay.
the other option is take this, what is it? Well, or take the number, you compute this, right? Assuming that there's no initial, you start with this. And then the coupling that you get, you will think about this as like an upper bound. So you can always have a smaller coupling, so you have an underabundance due to the themes. But then you have other mechanisms, so at the end you can fit the bill, right? So if you take this initial condition, which is what everyone does,
Okay.
then when you have the couplings, you have to think of the coupling as an upper bound. Yes. So, okay, let me emphasize this. So it really depends on initial condition, and people shamefully take this as zero.
Okay, thank you.
But yes, a good point. We have to, yeah, please remember that. Okay, now let's go, surprise, surprise, to the same beautiful model, singlet scalar dark matter. So what happens in the infrared themes in this scenario? So here's exactly the same Feynman diagram that I showed you yesterday, I think. So the dark matter S can be produced before the electroweak phase transition from annihilation of Higgs, right? In this plot here. So now let's think this from right to left. So production of dark matter via two scattering of Higgses. And after the electroweak phase transition, Higgs takes a wave, there's no mixing. And we can have this kind of process. So S-channel exchange of Higgs, T and U of S, and production from all standard model particles, so fermions and gauge bosons through the S-channel exchange of Higgs. Exactly the same as in the case of WIMPs. But now I'm showing you here the parameter space favored by FIMS, right? So the mass, dark matter mass in GV, right? So a big, much larger parameter space compared to the case of WIMPs. So maybe I should have started here at 10 to the minus 3 because of BBN. But I stopped here at 10 to the 6 GV, but I could have gone to even higher masses. But the important thing is the couplings, right? Couplings are not order 1 anymore, as in the case of WIMPs, but they're 10 to the minus 10-ish, right? So you can see like two regimes. Heavy dark matter, heavier with respect to the Higgs, correspond. In this case, dark matter will be produced via scatterings, basically. So mainly via these two scatterings, these two scatterings, these two scatterings. Whereas light dark matter, when it's lighter than the Higgs over 2, the Higgs mass over 2, is mainly produced via decays of the Higgs. So on-shell Higgs decay into a couple of dark matter particles. Okay? So a huge mass range, very small couplings, 10 to the minus 11 is the standard benchmark. Yes?
When the mass is very close, we have that thing, I don't know, the forbidden channels. Is this change the computation, or we have a resonance or something?
Yeah.
Can we trust this transition like that?
Of course.
But
No,
we need to
here is
change
not
something.
analytical. I use micromega. So I think micromega is
Okay.
taking care of all these thresholds.
Okay.
Yeah.
Okay.
Yeah, yes, this and yeah, I think micromegas from micromegas 5 it can compute freezing. It takes all your life, but you can do it. And here's exactly the same. So exactly the same model, the same parameter space, coupling as a function of the mass. I'm just showing you the two mechanisms. So these correspond to the plot I showed you before, so WIMPs. And here's exactly what I showed you before, I mean, the previous slide. So FIMS, right? So this is basically the plot I showed you before, right? So coupling as a function, it was mass here, no coupling, sorry, as a function of omega h squared. So this plot is basically cuts, vertical cuts, right? So I'm varying the coupling for a given dark matter mass. So just to emphasize the same point, so WIMPs is like order 1, and you have to be in the range of GV to TV. FIMS, so non-thermal production, happen at much smaller values of the coupling and for a huge range of masses. Yes? And again, here it depends, the theme depends on the initial condition, so please take this as an upper bound, right? So it could always be smaller if there are other mechanisms there, right? Active. Okay? Okay, now let's exploit a bit more the same coupling, the same model, sorry. We can see the different mechanisms. I will try now to combine mechanisms. Let's try to use, for instance, one particular case when you have infrared films plus SIMS. And I'm doing this because it's possible to do it in the same model. Okay, not yet. Okay, well, let's start it yet. So we have the model, we understand well the model. Here. So remember, we have the quartic couplings, and we have the Higgs portal. So this is kind of complicated plot, but let's focus on the left. So again, the same plot, yield as a function of x, right? And this blue line corresponds to the freezing, what we saw before. Yes? So you have the slow production, and at some point, you reach the plateau, freezing, boring freezing, and that's it. And that's in the freezing, for instance, we typically assume that the quartic couplings, or what we call lambda s, is equal to 0, because we are only focusing on the effect of lambda hs, so the portal. However, in general, we can see that we can think about the case where the two couplings are non-zero. And we can ask ourselves about the effect of having a non-zero quartic coupling, so non-zero self-interactions. So and that's exactly the case we're having. So infrared films, so small couplings, this lambda hs, and lambda s different from 0. So in the case where the quartic coupling is exactly 0, is the freezing, the blue line. However, if you allow this lambda x, so the quartic to be non-zero, is exactly what you were asking before. So you start having a production at a freezing, right? Then you can have the 2 to 4 interactions that enter into the game. So you have 2 to 4 interactions. You're producing dark matter, it's like self-production. Dark matter out of dark matter. So it's really 2 dark matter into 4 dark matter particles. So you're populating the dark sector, right? We have an increase of the dark matter. And at some point, you thermalize. Thermalization, you have this reaction that happen at the same rate. So you have first this, then you have the 2 reactions happen at the same rate, 2 to 4. And that is exactly the WIMP mechanism, right? So you have a plateau, because dark matter is relativistic. This smoking is because of change of relativistic degree of freedom, doesn't matter. So important, you increase because of 4 to 2, you have a plateau because you reach equilibrium within the dark sector. So 2 to 4 and 4 to 2 happen at the same rate. When dark matter, then at some point dark matter becomes non-relativistic, and you see here a very small suppression. It's a Boltzmann suppression, right? But it's, I mean, I'm scanning over 8 decades in yield, so you cannot see. But here, this piece is the Boltzmann suppression, right? So in this third moment, what you really have is 4 to 2. 4 to 2 annihilations, like the freeze out, right? And then we reach a plateau, the freeze out. Yeah? So here is really, you can see in the same model, right, singlet scalar dark matter model, the same that we have already using, interplay between FIMS and SIMS. Because in general, that's what you could expect, right? If this guy is small but non-zero, and this guy is non-zero, you could have this kind of behaviors. And here I'm showing a plot of the temperature as a function of x, so the inverse of the temperature. So by construction, T is the temperature of the standard model. It goes like 1 over x, just by construction. So T, so the dashed red line corresponds to the evolution of the standard model temperature. very boring, just a power law by construction. And this T prime in black corresponds to the evolution of the temperature of a dark sector. So at some point at the beginning, they have basically the same temperature. And you can see when you have 2 to 4, you're creating dark matter from temperature, right? So you're going from 2 relativistic dark matter particles into 2 non-relativistic. So you're decreasing the temperature, the energy. So the temperature, and that's why you see here a drop in the temperature, so the dark sector cool down. Then you have equilibrium, so it's relativistic in equilibrium. So it's exactly the same scaling, so 1/A. So these 2 lines are supposed to be exactly parallel. Then what you have is 4 to 2, is what we saw last time, yeah? So you're trading mass into kinetic energy. So 4 non-relativistic particles into 2 relativistic particles. Energy increase, so temperature of the dark sector increases. And then you're out of equilibrium, you're non-relativistic, temperature goes like 1/A scale factor square, just redshift of momentum. Yes? Here or where? Yes. Yes, so yes, it's very abrupt here, but also here. Huh? So it's like an explosive production of dark matter via this process. Yes. So exactly the same, right? So you can basically translate one to the other. So you produce a lot of dark matter particles. That means that the temperature has to go down very fast as well. Okay, so remember I told you that WIMPs were kind of independent on the initial conditions. So we have this plot, the same as the WIMPs as usual, blah, blah. And I told you that it's independent of initial conditions, that if I start here or here, the result will be the same because you reach equilibrium very fast. Or if you start here, for instance, the equilibrium will be reached very fast. And that's exactly the same. So it's very effective in reaching equilibrium, and that's what you can see there. But I agree, this is kind of surprising, right? This seems like an adiabatic process. Yes?
Can you explain again why in the beginning we have 2 to 4 there? Like
Okay. Yes.
why it's
Yes, because, yes.
like
Okay, at the beginning, you don't have equilibrium, basically because you have a dark matter underabundance with respect to equilibrium. So you have very few dark matter particles, right? You can see. Here you have very few dark matter particles with respect to equilibrium. Okay, this I will confuse you with this. This, I don't know what is this color, blue dashed line is the equilibrium with respect to the dark sector. It's super weird because the dark sector have a different complicated evolution of the temperature, but this is the equilibrium. So dark matter is you have an underabundance with respect to equilibrium, right? So 4 to 2 will be very suppressed because basically you have no dark matter particles, very few dark matter particles. So you can have the 2 to 4, but 4 to 2 is very suppressed because you don't have enough. So at the very beginning, you only have this reaction in place. Very fast you thermalize, and you have both happen at the same rate. But at the very beginning, you have only this, then you thermalize, you have both, then it becomes non-relativistic, and you only can have this one.
No, yeah, I'm just thinking because I cannot see like exactly with the equation because the rates, both rates depends on n dark matter. But the 4 to 2 is, it's because the 2 to 4 is squares with n dark matter, and 4 to 2 is square with n dark matter to the third, for example, and then because this is very small. Is this the explanation?
Yes, exactly. This
yeah,
is basically the same cross sections.
I'm thinking about the rates.
Yes.
That's the explanation. Because thinking about like the cross section, the phase space, we wouldn't think that it would go in this direction. But if you think about
it's just rate is basically a cross section times
yes.
number density. So here will be number density square, his number density power 4.
Yeah.
So this is very suppressed at the very beginning because of number of particles.
Yeah.
So
I
same
can-
cross section, but smaller
but
luminosity
so I
if you
can
want.
explain with the rates, like thinking about the rates.
Exactly,
Yeah. Okay,
exactly the
I
rates.
understand.
Yes, yes. Yeah, so here this one dominates, here the rates are exactly the same, and here is this one which is dominant. Yes, thanks. And okay, so exactly the same model, the same plot as before. So dark matter mass, quartic coupling, and the required values of the portal. Yes? So we have first production at a freeze-in, very small Higgs portal, and order 1 values for the quartic coupling. Yes? So it's really an interplay between FIMS and SIMS in the same model. Okay? So that's all that I want to tell you about infrared FIMS. Now, if there are infrareds, surprise, surprise, we have ultraviolet FIMS. And we'll use a parallel with respect to the infrared. So I start renormalizable. We'll have non-renormalizable operators. So we'll typically think about this sigma v, that was work quantity, or the interaction rate. Now we want it to be suppressed by a large scale, say t power n plus 2 by dimensional analysis. So we assume lambda is a scale of new physics, right? Very large with respect to the other scales, in particular to the temperatures. So lambda wants to be much higher than, oops, that's not lambda, than T reheating, the temperature, the onset of the radiation domination, or T max, so much higher than on all other scales in the process, right? And so it has a strong temperature dependence. So remember that by this guy, sigma v depends on the temperature, right? So we'll parameterize it in this way, and I can give you some examples. So non-renormalizable operators, small couplings. We don't have here small couplings, but large scales, right? So and remember that what we want to do is we want to avoid thermalizations. So we want small interaction rates. So small interaction rates mean small lambdas, small sigma v's. Small sigma v's could be generated if you have small couplings, small numbers upstairs or very large numbers downstairs, right? So there's no mystery here. The mass range is basically the same. Mass is, say, MEV to a large number. Let me put Planck mass, whatever. Okay, and the bulk of the dark matter in this UV is produced at the UV. So when the temperature is of the order of, say, T reheat, or the highest temperatures reached by the thermal bath. Initial conditions, again, that's not surprising. Again, it's a non-thermal process. You have a strong dependence on the initial conditions. And here it's even worse than maybe than the infrared case, because it really depends. You have a strong dependence, again, on T reheat, T max, maybe the equation of state of the universe during reheating, omega, reheating, blah, blah, blah. All the reheating dynamics will be encoded in the solution of this ultraviolet freezing. I have a plot. So remember how was infrared films produced? So we have a small, slow increase in the abundance, and then you reach a plateau. For the infrared, for the freeze out, for the freezing ultraviolet, it's an explosive, right, production. So again, the same parameters place. So y, now as a function of temperature, sorry, and temperature is decreasing. Sometimes it's flowing from left to right. Temperature is decreasing, 10 to the 10, 10 to the 9, 10 to the 8. And I'm showing you here the evolution of the co-moving dark matter abundance for different values of n. Remember, I'm parameterizing. N is basically the dependence on the temperature of this operator. And you can see it's really explosive. So it started at 10 to the 10. It was just a choice. And you can see that the bulk of the dark matter production happens really at the ultraviolet, so at the highest temperature. So basically at my initial condition. So the bulk appears here. So it's an explosive production. And if I try to solve this this equation, so here I'm showing you the plot of gamma, of lambda, sorry, so this scale of new physics, as a function of the reheating temperature. Yes, so this reheating temperature, if you want, for me is the initial condition. So you can see that in order to fix the dark matter abundance for different values of n, I have to play both with the particle physics, right? So with my operator, but also with the cosmology, right? So this is the initial condition. So I'm always assuming that I don't have any production at the very beginning, so that all is produced via this process. However, there's a strong dependence on the reheating temperature. So basically, where I'm starting the evolution. Yes. Okay. Yeah, no, okay, no. Sorry, no. So here in the left, I'm changing lambda. I just want to, here the idea was just to show how it evolves. The point is it evolves very fast at the very beginning, and that's it. But yes, I'm kind of cheating. I'm using different values of lambda. Yes, so the infrared is kind of difficult to solve analytically, so that's why I didn't do. The UV freezing is very easy. You can do. I just forgot to give you the expression. I didn't, but very easy. You can do it really analytically. It takes half a page. You can solve this, and you will find that the yield will depend, of course, on the operator, but you will have a strong dependence on T reheating, explicit dependence on T reheating. There. Yes, maybe I should have computed here for you guys. Okay, so I have like 15 minutes. So questions?
Sorry, I didn't understand why it depends on T reheating. Is where you start the initial condition, like you said?
Yes, but
at T reheating, that's the thing?
I have to say, so these are the differential equation, right? So you have to evolve from initial time, from initial temperature. Exactly. Yes, so it could be more complicated than that, because you can have production really during reheating. But as a first approximation, let's assume that the reheating is instantaneous or very short. So that dark matter is only produced in the radiation domination, right? So in that case, the highest temperature reached by the universe is T reheat. So yes, but it could be much more complicated than that, and I will discuss tomorrow about the possible production during reheating.
But in principle, this look at this moment very different than putting the abundance by hand.
Than putting what?
The abundance by hand.
Yeah.
As long as you know it's not thermally in equilibrium, just put it. You can say it's because it comes from instantaneous reheating, but essentially it's not very different than saying I just put it there.
Yeah, no, at this level, you're really putting that by hand. Of course, if you have an inflationary model, you have a cosmological model.
At this point, it's just saying, I can put it by hand by saying that it's instantaneously produced at reheating temperatures that are high enough.
Yes, I mean, if you stick to your hardcore particle of physics, this is just a number that, that you don't know. You can parameterize the identity of the early universe just varying this quantity. Yeah.
You're saying like that if you choose, you can choose to set, like only with this reheating you set the correct dark-matter abundance in this case, for example?
Yeah, for instance here, so you can, if you fix your particle physics, meaning you fix your operator, you fix your lambda, you can know what is the required T reheated in order to reproduce observations. We don't know, it has to be higher than MEVs. Yeah. So, yes, just to emphasize this point. Very important, depends on the initial condition. And we don't know, right? So you have no control on that. Okay, that was everything I want to tell you, I think, about non-thermal production and FIMS. So you have like 15 minutes. Okay, we have basically focused till now on the, remember the very beginning. So we want to compute the dark matter abundance, and we had two operators with the Liouville and the collision. So here, till now, we have focused really on the collision operator. So we have been playing with the particle physics. And we have seen this number of different mechanisms, the FIMS, so thermals and non-thermals. So WIMS, annihilation, self-annihilation, semi-annihilation, co-annihilation. And then we saw elders, cannibals, what else? SIMS, and then non-thermal. Okay, we discussed last week with Kafir, fuzzy dark matter, and now we saw FIMS in the two versions, UV and infrared. So everything, they all correspond. We were playing with the collision operator, right? So we can also have fun with the Liouville operator. So we can also think about possible non-standard cosmological evolutions, and that's what we will discuss now. So Cosmo, very fast, in 5 minutes. So what we have done so far, we have assumed that the universe is always dominated by standard model radiation, right? So we assume always that H of T, let me put it like this, is pi over 3 G star over 10 square root T square over M Planck. That we have always used. That means that the universe is dominated, we have assumed that it's dominated by standard model radiation. The Hubble expansion rate is dominated by not only radiation, but standard model radiation. But we have also assumed another thing. So first point, we have assumed that the standard model entropy, standard model, is conserved because all processes are adiabatic. This is what we have always explicitly assumed. I remember I make a big deal when computing the Boltzmann equation for WIMS. And why we're assuming that? I mean, in the early universe, we kind of understand how it works from the scale of BBN. So we know, we're kind of sure that this is guaranteed if the temperature is smaller than the temperature of BBN. So in the MEV scale. So this is what we assume in the standard cosmology, called standard. So what the standard cosmology, the assumption of standard cosmology is that these two things, these two conditions that we know that are fulfilled after BBN, we make a shameless extrapolation. We say that if this is the case from BBN, it should also be the case before BBN. Of course, there are two assumptions that are completely not under control. It makes sense because it's like the minimalistic. If you take a minimalistic approach, it makes completely sense. However, this is not guaranteed, right? And we know for sure that these conditions are both violated in the very early universe. For instance, during reheating. During inflation, of course, because during inflation, the Hubble expansion rate was not dominated by standard model radiation because they were not standard model radiation. It was dominated by the inflaton, so we have inflation, right? And during reheating, the standard model entropy was not conserved because we have the energy injection of the inflaton. So inflaton is decaying or annihilating or who knows what, and producing a standard model. So the standard model entropy was not conserved. So we know that there are stages in the early universe where these conditions are violated. So we'll study some very simple and I think well-motivated cases when we can have deviations from this standard cosmological scenario. And we'll see a couple. Okay, so the first will be early matter domination. Do, mi. So we can imagine that the early universe was eventually dominated by a non-standard model particle, right? With a non-relativistic, so with an energy density that scales like matter. So remember, the standard model, okay, radiation, in particular, a standard model, okay, what I call R, goes like 1 over scale factor power 4, A, the scale factor of the universe. It's radiation, so it scales like 1 over scale factor cube because it's the volume, but also redshift, so it's A power 4. However, matter goes only like a cube. It's matter, it's not redshift, it's just expansion, right? So it's the volume. That means that radiation, its energy density tends to be subdominant at some point with respect to matter. Yes, because it gets diluted faster. And that's why, for instance, we have the matter radiation equality in the early universe, because at some point dark matter becomes to be the dominant component. But that's not the idea. We can imagine that in the early universe we have a heavy guy, which is long-lived, a lifetime typically, say, seconds, right? And then, because its energy density scales like a cube, 1 over a cube, it can eventually dominate the total energy density of the universe. So that's the idea. Let's suppose that we have a heavy guy with a large lifetime, say 1 second. That's enough. And heavy guys we have, I mean, they're super abundant. I mean, if you have God theories, or you have moduli, or even you have like a right-handed neutrino. So with a heavy mass, we have a high occupancy. It could naturally dominate the total energy density of the universe because of this, because of scaling, because it's a non-relativistic particle. So we can track the evolution of the number density of this guy that we'll call phi, which is, yes, phi, this heavy guy with a long lifetime. So its number density of phi dt is basically the Boltzmann equation that we have seen 100 times, right? 3h and phi. 3 because it's matter, right? 3 dimensions in the space. So the Liouville operator is exactly the same. And we will assume that this guy, phi, eventually will decay into 2 standard model particles, right? With a decay with gamma phi. So it's a decay. So it will decay, so it will be minus gamma phi and then phi. Yes, we can. That's the Boltzmann equation for its number density. So this guy is decaying into radiation, into standard model radiation. So we can write the equivalent for the number energy density of radiation. And, no. So so this is slightly different as we have seen before. So is the variation, the time variation of the radiation, standard model radiation energy density. This Liouville operator is slightly different. This 4 basically comes from here, right? So it will decrease because of the increase of the space, but also because of the redshift. So it's a 4 here, and plus gamma phi n phi, me falta uno, m phi. Okay, this guy has a mass m phi. So that what it's basically telling us is that so when this guy decays, when phi decays, it injects entropy into the dark sector, right? So these terms are basically the same. So it's energy density, so I have to put a mass. This is basically the energy density of phi. It's minus because it's losing energy, because it's decaying, plus because it's winning energy, right? Because you have an entropy injection. So phi decays into standard model. So these two equations are coupled because of the source term, but also because of Hubble. Because Hubble square, we have to include all the species, all the energy density. So we have radiation as before, but also this guy phi with an energy density which is m phi times n phi over 3 m Planck square. Oops, like this. This is the Friedman equation. They could all have put curvature, but I mean 0, cosmological constant, but at these stages is completely subdominant. So these guys will give you the evolution of actually these 3 equations of the background. How the energy density, the number density of this guy is evolving, how the energy density of radiation is evolving, and this how the universe is evolving, the expansion. And the important thing is that this guy could naturally dominate at some point if it's long-lived enough. Yeah. And I think I have a plot. Yes, it's a complicated plot, but because I took into account the degree of freedom. But you will see, it's very simple. So let me do again this, the plot on the left. So a simplified version, so a scale factor and energy densities times energy density times scale factor power 4. So you expect, so free radiation scales like 1 over scale factor 1 over A4. If I multiply by A4, I got a constant. Yes, that's what I expect. Let me put it in dotted. Yes. So at first, so before this guy is dominated, when the universe is dominated by standard model radiation, that's what I get for rho r. This guy phi scales like 1 over a cube. If I multiply by a4, you will have an increase in yellow, rho phi. And this guy, okay, let me do, so at some point you will get an equality between the 2 energy densities. This guy, so it will be something like this. Yes, it always scales like a cube, 1 over a cube, and at some point it decays. This guy will continue like this. It will increase, and then like this. Yes, so there are like 3 important scales. At first, you will have an equality, and I call the equality, surprise. Yes. Then at some point, the universe starts to be dominated. So this part here is what they call the early matter domination, because the Hubble expansion rate is dominated by phi and not by radiation. However, there are 2 interesting regions. So we have like one adiabatic region where the energy density is dominated by phi, but it's effectively not decaying, not a sizable decay. So the radiation has no source. So this is adiabatic, and this is non-adiabatic. When phi really is decaying, it's injecting entropy into radiation. So the radiation will have a different scaling, different than the expected scaling, because it has a source. So radiation scales like 1/A4 is free radiation, really, not always. So this is basically what you see there, right? So matter domination, early matter radiation domination, sorry, radiation domination, matter domination, and radiation domination back. Yes, and 2 epochs in the early matter domination, adiabatic and non-adiabatic, depending on whether the guy is effectively decaying or not. And this is basically the same plot there as in the right. So evolution of the temperature times A. You expect temperatures to go like 1/A. So if it's times A, you will expect like a constant behavior. And the 3 scales here. So you expect something like this. So early matter domination, radiation, and radiation. And you have a funny moment where the energy is not, the temperature, sorry, is not scaling at 1/A. Why? Because it has a source. So the phi is decaying into radiation. So it's injecting entropy. So it's producing more photons, if you want, more standard model particles. So the temperature will have a funny scaling. So it's never increasing, really. The temperature is never increasing. It's just it's decreasing less fast than expected. And then you recover the radiation domination. Yeah.
I didn't understand how the energy density of phi is increasing from the equations. What is...
Because exactly you have a source term here.
But this is for the radiation.
Phi, you say?
Phi, yeah, for phi.
No, it's not increasing.
But,
Okay,
why?
there. Okay,
Yeah,
no, it's just a trick. It's that you expect phi to go like 1 over the scale factor cube.
Okay.
But I'm multiplying by
okay.
4.
Sorry. Now I
Yes,
understand.
sorry. It's never really,
Okay,
it's never increasing.
okay,
Yes,
okay.
sorry,
Just
it's a trick.
check. And then, can you repeat the second moment? Like the first is the equality, and then there's the yellow dotted line. This
Yes,
one.
so that's
sorry,
what
what happened there?
So
exactly
it's
happened?
always dominated by phi. However, at the very beginning, you can see that you can think that it's not effectively decaying. Of course, it's an exponential decay. It's always decaying. But think that it's effectively not decaying. So it's dominating the energy. So Hubble is different. However, the scaling of the temperature is the same, because photons really don't feel, so radiation is not really feeling that the guy is decaying, because it's not decaying. Just to me, it's not decaying. Effectively, it's not decaying. So it's an adiabatic era in that sense. Phi is effectively not decaying, so the standard model temperature scales like 1/A, as expected. It's really free radiation. Where at the very end, this guy, phi, really starts to decay. So it's non-adiabatic era, and you can see it because the standard model temperature is not scaling at 1/A anymore, because it's not free radiation. It's a radiation with a source term.
Okay, I think I need to think. I didn't understand what physically happened. Like, just it's not clear to me.
It's just this.
Why is this value exactly?
Which value?
Yeah, the value where the threshold, like in the equations, I cannot see.
Okay, you can compare,
want
you
to
can know, you
understand.
can compute that,
Maybe it's
comparing
not,
these two terms.
Okay, it's not like
So-
it's not straightforward. Probably you need to solve the equation.
Well, you can solve the equations numerically, but then they're a bit complicated. But also you can do that analytically. Yeah. So you can compute, for instance, all these slopes. So here is t goes like 1 over a. Here t goes like 1 over a, 3 over 8. T goes like 1 over. And you can compute all these powers. And this will depend, for instance, on the equation of state. I assume it's radiation, but in general it could be another equation of state, and also on the decay width. The decay width, I'm assuming, is constant, but it could have a non-trivial dependence. It could depend on the field, for instance.
Okay.
So I don't think I have much more time, no?
I mean, you have an entire new thing to say, or is some final?
Final remarks? Thank you.
Ah,
No,
okay.
I can
Thank you.
continue next time.
Okay, thank you.
Thank you.
Some more burning questions?
Just, so this phi field, it just exists in the early universe. It's
Yeah,
not created.
think of right-handed neutrino, something like standard, right? For leptogenesis, so its mass is 10 to the 10 GeVs, whatever, and its lifetime is 1 second, 1 minute. That's enough.
But it is not created with this radiation, from the standard model radiation.
Say it again.
Like it is not created from the standard model radiation.
Okay, how these guys produce, that's another story.
Yes.
Yeah, it could be, no, it cannot, can it come? I think so. It can also be produced by, yes, from a standard model radiation. Yes, because even if it's, I mean, the point is that it could be very subdominant, completely subdominant at a very early universe. But if it's not relativistic, its energy density scales differently. So it can naturally become dominant, even if at the very beginning it's completely subdominant. Well, like dark matter, right? So it could be subdominant, and at some point you have the quality.
So where does dark matter fit in this picture?
No, my point is that you have also an equality between radiation. Okay, forget everything. Sorry, I don't want to confuse you. I mean, in the late universe, you have the radiation equality, right?
Mm.
And it's because of that, because the two different scalings. But yes, sorry, I don't want to confuse you.
Okay, thank you.
More questions? No? Okay, so let's thank Nicolás again.